The universe is hiding its true nature in plain sight. We will explore 15 deep space anomalies that defy our understanding of modern physics. These are not small curiosities, but colossal mysteries that force scientists to question the very foundations of reality. You will gain a front-row seat to the greatest cosmic puzzles of our time, from invisible forces tearing space apart to ancient structures that should not exist. Why do the outermost stars of galaxies race around as if gripped by unseen hands? What could send a single particle hurtling across the cosmos with the energy of a fastball? This exploration pushes the boundaries of human knowledge, revealing how much of the cosmos remains a breathtaking enigma. What do you think is the universe's most carefully guarded secret? Our entire visible universe is just a fraction of the cosmic story. Every star, every planet, every swirling nebula you can see through a telescope accounts for less than 5% of everything that exists. The rest is a profound mystery, a missing chapter in the book of reality. For decades, the most glaring evidence of this has been a ghostly presence known as dark matter. Think of a galaxy like a giant merry-go-round with stars as the riders. According to the laws of gravity we understand, the stars on the outer edge should be moving slower than those near the center, just as planets farther from the sun orbit more slowly. But in the 1970s, astronomer Vera Rubin made a startling observation. She found that stars at the very edges of spiral galaxies were whipping around at nearly the same incredible speed as those close in. It was as if the entire galaxy was embedded in a vast, invisible sphere of something massive, its gravity gripping the outer stars and preventing them from flying off into the void. That something is dark matter. It does not emit, absorb, or reflect light. It is completely transparent to every form of electromagnetic radiation we know. We cannot see it, but we can see what it does. Its gravitational fingerprint is everywhere. One of the most dramatic pieces of evidence comes from a phenomenon called gravitational lensing. The immense gravity of a massive object, like a cluster of galaxies, warps the fabric of space-time around it. This acts like a giant lens in space, bending and distorting the light from even more distant galaxies behind it. By studying these distorted cosmic mirages, scientists can map the distribution of mass in the foreground cluster. Time and again, these maps reveal far more mass than the visible stars and gas can account for. The lens is being shaped by something unseen. So what could this invisible substance be? The leading candidates are exotic particles that hardly interact with normal matter at all. One group is called weakly interacting massive particles, or WIMP for short. These are theoretical heavy particles that would only rarely bump into the atoms of a normal detector. Another candidate is the action, a hypothetical particle so incredibly light and ghostly it could pass through entire planets without a trace. For over 30 years, incredibly sensitive experiments deep underground have been searching for the faintest whisper of a collision with a dark matter particle. So far, they have found nothing definitive. This relentless silence is itself a profound clue. It tells us that dark matter is not just hidden. It is fundamentally different from anything in our current inventory of particles. It forces us to confront the possibility that most of the universe is made of a substance we do not understand, a form of existence that operates by rules we have yet to write. And if the mystery of dark matter is about missing mass holding things together, the next anomaly presents the opposite puzzle, a force that seems to be tearing everything apart. Gravity should be the universe's ultimate brake. After the immense energy of the Big Bang flung everything outward, the collective pull of all matter, both seen and unseen, was expected to gradually slow that expansion. The fate of the cosmos was a question of density, whether there was enough gravity to one day pull everything back in a big crunch, or if things would coast to a gentle, frozen halt. Then, in the late 1990s, two independent teams of astronomers made a measurement that shattered that entire picture. By studying distant stellar explosions called Type 1 a supernova, which act as cosmic mile markers and standard candles, they sought to measure how fast the universe was expanding in the past. Their results were not just surprising, they were revolutionary. The most distant supernova, whose light had been traveling to us for billions of years, were fainter than expected. This meant they were farther away than our models predicted. The expansion of the universe was not slowing down, it was speeding up. Some mysterious repulsive force, acting against the pull of gravity on the largest scales, was pushing galaxies apart at an ever-increasing rate. This discovery earned the researchers the Nobel Prize and introduced the world to the dominant component of our reality, dark energy. Think of space not as a passive stage, but as an active participant. Empty space itself, according to one leading theory, possesses a fundamental energy density. This concept, called the cosmological constant, was actually introduced by Albert Einstein in his equations of general relativity to allow for a static universe. When Edwin Hubble later proved the universe was expanding, Einstein famously called the constant his greatest blunder. Now, it appears he may have been right for the wrong reason. This energy of the vacuum, a gentle pressure inherent to space, would cause expansion to accelerate. But when physicists calculate what this vacuum energy should be based on quantum theory, the number they get is wrong by a factor of 1 followed by 120 zeros. It is arguably the worst prediction in the history of science. This staggering mismatch has led to other ideas like quintessence, a dynamic energy field that changes over time, or even modifications to Einstein's theory of gravity itself. Whatever its true nature, dark energy is not a minor player. It constitutes roughly 68% of the total mass energy of the universe. It is the primary architect of our cosmic fate, dooming the universe to expand forever until galaxies are isolated islands, their stars burning out in an ever-cooling, ever-darkening void. This immense, smooth force acting across the cosmos stands in stark contrast to the next anomaly, a violent and deeply localized rebellion against gravity's rules. Even the most meticulously planned journeys can reveal an unexpected detour. For over 30 years, two robotic explorers, Pioneer 10 and Pioneer 11, charted a silent course into the outer solar system and beyond. Their mission was to study Jupiter and Saturn, but they left behind a legacy far stranger than anyone anticipated. As they drifted toward the edge of our sun's influence, something was wrong. By tracking the faint radio signals from the spacecraft, scientists led by researcher John Anderson could measure their velocity with incredible precision. The data showed a persistent, tiny deviation. The probes were slowing down slightly more than they should have been, as if an unseen hand was applying a gentle, constant tug back toward the sun. This was the Pioneer Anomaly, an acceleration so small it was equivalent to the weight of a single grain of sand pressing on your hand, yet it was undeniably there. For decades, this minuscule drift defied explanation. Was it a flaw in our understanding of gravity itself on the vast, lonely scales of deep space? Some theorists suggested that the laws of gravity might need subtle modification at great distances, a revision that could ripple through all of cosmology. Others looked for more conventional causes within the spacecraft. Every component was scrutinized. Could the faint heat radiating from the spacecraft's electronics and nuclear power source be pushing back on the probes like a tiny photon rocket? After years of painstaking analysis, this thermal explanation emerged as the most likely culprit. The anisotropic, or uneven, radiation of heat was creating a tiny but measurable recoil force. The Pioneer Anomaly stands as a masterclass in scientific diligence, a reminder that even the smallest signal must be traced to its source. It was likely a case of celestial engineering, not new physics. Yet its shadow lingers. It taught us to measure with obsessive care because the next unexplained push might not be from a warm battery. It might be a whisper from the universe itself, hinting at forces we have not yet imagined. And if a gentle tug on a spacecraft is puzzling, the next anomaly represents the opposite extreme, a cosmic event of such raw, unfathomable power that it seems to break every rule of physics we have. A galaxy in motion is a cosmic clockwork of staggering beauty and predictable order, or at least it should be. For centuries, our understanding of celestial mechanics was built on a simple, elegant principle, the same one that keeps planets in orbit around our sun. The closer you are to the gravitational center, the faster you must travel to avoid falling in. Mercury whips around at a blistering pace, while distant Neptune plods along in a slow, stately dance. Apply this logic to a spiral galaxy, a disk of billions of stars, and you would expect a clear gradient of speed. The stars near the bright, crowded core should be racing, while those far out in the sparse, dark spiral arms should be drifting along leisurely. This prediction forms a specific shape on a graph called a rotation curve. It should rise steeply near the center and then fall away in a clean, declining slope. But the universe had a different, far stranger curve in mind. When astronomers like Vera Rubin began meticulously measuring the orbital speeds of stars in galaxies like our neighbor Andromeda, they found something that defied this elegant prediction. The rotation curves were not falling slopes, they were flat. Stars tens of thousands of light years from the galactic center, in regions where visible matter was thin, were orbiting just as fast as those nestled close to the brilliant core. It was as if every star, from the innermost to the outermost, was embedded in the same relentless gravitational grip. The visible galaxy, all the stars and gas we could see, simply did not contain enough mass to explain this. According to the established laws of gravity, those outer stars should have been flung into the intergalactic void long ago. The only way to explain their breakneck speed was to propose that galaxies are enveloped in vast, invisible spheres of something else, halos of non-luminous matter exerting a tremendous gravitational pull. This was one of the first and most powerful pieces of evidence for what we now call dark matter. The implications of this flat curve are profound. It suggests that what we see when we gaze at a magnificent spiral galaxy is merely the luminous tip of a colossal, hidden iceberg. The beautiful pinwheel of stars is just a small structure embedded within a gargantuan, diffuse cloud of unknown material. This idea is so radical that some physicists have pursued a completely different path, questioning not the contents of the universe but the rulebook itself. A theory known as modified Newtonian dynamics, or MOND, proposes that our understanding of gravity is subtly incomplete at the extremely low accelerations found in the outer reaches of galaxies. In this view, gravity behaves differently when its pull becomes incredibly faint, providing an extra boost that keeps outer stars moving fast without the need for invisible mass. It is a compelling alternative, a tweak to the equations rather than an invention of new substance. This creates a fundamental conflict at the heart of modern cosmology. Do we accept that most of the universe is made of a mysterious substance that refuses to interact with light? Or do we rewrite the laws of gravity, a foundation of physics that has proven spectacularly successful everywhere else? The flat rotation curve of galaxies forces this choice upon us. It is a silent, persistent signal written in the motion of stars, a direct challenge to our maps of reality. While this anomaly sculpts the grand architecture of galaxies, our next discovery zooms in to reveal a different kind of defiance, a single point in space where the laws of physics seem not just stretched but completely suspended. Our galaxy is not a stationary island in the cosmos. It is a traveler on an immense river caught in a flow we cannot see. The Milky Way, along with our entire local group of galaxies, is hurtling through the universe at a staggering speed of over 600 kilometers per second. For decades, astronomers traced the source of this motion to a mysterious, hidden concentration of mass in the general direction of the constellations Centaurus and Hydra. They named it the Great Attractor. Picture the most powerful gravitational sink imaginable, a place where the fabric of space-time itself is pulled into a deep well, drawing thousands of galaxies, including our own, toward its unseen center. This was the cosmic tug-of-war governing our journey, but there was a profound problem with observing it directly. The Great Attractor lies in a region of the sky called the Zone of Avoidance. This is the dense plane of our own Milky Way, thick with interstellar gas and dust that completely blocks our optical view, like trying to see a distant mountain through a dense, personal fog. For years, the true nature of the attractor remained hidden behind this celestial veil. To map these invisible flows, scientists turned to a clever method. They study the peculiar velocities of thousands of galaxies. This means measuring not just how fast a galaxy is moving away from us due to the universe's expansion, but the extra motion superimposed on top of it, the drift caused by local gravitational tugs. By charting these subtle deviations across the sky, astronomers can create a three-dimensional map of the gravitational landscape, revealing hills of mass and valleys of emptiness. This painstaking work led to a second, equally startling discovery. Our motion is not just caused by what is pulling us, but also by what is pushing us. Behind us, in the opposite direction from the Great Attractor, lies an immense, almost empty void now known as the Dipole Repeller. Think of it as a cosmic desert of staggering scale, a region so devoid of galaxies and matter that its gravitational push, or more accurately its lack of pull, contributes significantly to our galaxy's rush toward the attractor. We are being shoved from an empty place as much as we are being pulled from a full one. Together, these structures are megastructures in the cosmic web, composed of thousands of galaxies and truly colossal amounts of dark matter, their gravitational influence sculpting the motion of everything around them for hundreds of millions of light years. They remind us that our place in the universe is dynamic, swept along in currents set in motion by the largest structures in existence. While these titans of mass and void shape our grand trajectory through space, other anomalies challenge our understanding not with gravity's pull, but with light's pure, inexplicable fury. The quiet hum of a cosmic background is occasionally shattered by a messenger of unimaginable violence. From the depths of space, a single subatomic particle, often just a lone proton, can arrive carrying more kinetic energy than a major league fastball. These are ultra-high energy cosmic rays, and their existence pushes the boundaries of what we believe is possible in the universe. To catch these elusive particles, scientists have built the world's largest particle detectors on the ground, like the Pierre Auger Observatory in Argentina. It spans an area of 3,000 square kilometers, an array of over 1,600 water tanks and telescopes watching for the faint, cascading showers of secondary particles created when one of these cosmic bullets slams into our atmosphere. Even with this vast net, they detect only a handful of the most energetic events each year. Their rarity is a clue to a profound mystery. According to a fundamental limit in physics known as the Greisen-Zatsepin-Kuzmin, or GZK cutoff, such particles should not be able to travel vast cosmic distances. The space between galaxies is not completely empty. It is filled with the faint afterglow of the Big Bang, the cosmic microwave background radiation. A proton traveling at over 99.9999% of the speed of light should constantly collide with these background photons, losing energy like a spaceship plowing through a thin, persistent fog. Over distances of more than a few 100 million light-years, it should be slowed to a crawl. The fact that we detect them at all means one of two startling things. Either these particles come from relatively nearby sources within our own cosmic neighborhood, defying the GZK limit, or they come from farther away, which means something is fundamentally wrong with our understanding of how particles lose energy on their epic journeys. So what cosmic engine could possibly accelerate a single particle to such insane energies? The candidates are as extreme as the particles themselves. One leading suspect is the active supermassive black hole at the heart of a distant galaxy, an active galactic nucleus. The chaotic, magnetized maelstrom around such a black hole could act as a natural particle accelerator of staggering power. Another possibility is the catastrophic collapse of a massive star into a black hole, a gamma-ray burst which could channel a focused jet of energy capable of this feat. Some theorists even look beyond conventional astrophysics, suggesting these particles could be the decay products of super-heavy dark matter particles, relics from the universe's first moments annihilating in the halo of our own galaxy. Yet pinpointing the source is maddeningly difficult. Unlike light or gamma rays which travel in straight lines, cosmic rays are charged particles. As they streak across the universe, they are deflected and bent by the weak but pervasive magnetic fields that thread through interstellar and intergalactic space. By the time one reaches Earth, its path is so scrambled it is like trying to trace the origin of a leaf caught in a hurricane. The arrival direction tells us almost nothing about where it began. Each detection is a shout from the void with no return address, a signature of a cosmic catastrophe we cannot yet locate. These particles represent the upper limit of nature's particle accelerators, far exceeding anything we can build on Earth. Their very existence is a direct challenge, forcing us to ask what unimaginable events are occurring in the hidden corners of the cosmos. Events that can hurl a single speck of matter with the force of a pitched ball across billions of light years. While these particles speak of isolated moments of extreme violence, our next anomaly reveals a pattern on a scale so vast it seems to orchestrate the cosmos itself into a rhythm we are only beginning to hear. The universe is capable of symphonies of destruction, but sometimes it chooses a single, deafening note. In 2007, astronomers sifting through archival data from the Parkes Radio Telescope in Australia found something that should not have been there. A spike of radio energy so intense, so fleeting, that it lasted just 5 milliseconds. In that blip of time from a source billions of light years away, it released as much energy as our Sun does over 80 days. This was the first recorded fast radio burst, and it opened a window into one of the most extreme and mysterious phenomena in the cosmos. These FRBs are not gentle signals. They are cosmic screams erupting across the universe without warning, their origins completely hidden. Since that first discovery, hundreds have been detected, and they come in bewildering variety. Most are one-off events, a single brilliant flash from a distant galaxy that never repeats, but a precious few, like the famous repeater known as FRB 121102, defy this pattern. They fire off again and again, in seemingly random sequences, allowing telescopes to finally triangulate their position to a specific, tiny dwarf galaxy over 3 billion light-years away. This ability to locate a host galaxy was a monumental breakthrough. It confirmed these were not local glitches or instrumental noise, but genuine astrophysical events of staggering power emanating from the distant universe. So what natural engine could possibly create such a brief, titanic blast? The zoo of theoretical explanations is as wild as the bursts themselves. One leading candidate is the magnetar, a type of neutron star with a magnetic field so powerful it could strip the information from a credit card from halfway across the solar system. A starquake on the surface of such an object, a sudden cracking of its crust under immense magnetic stress, could theoretically unleash the focused radio flash we see. Other theories point to cataclysmic finales, like the collapse of a supermassive star into a black hole, or the violent merger of two neutron stars. There are even more speculative ideas on the fringe, including the possibility of advanced extraterrestrial technology, though most scientists consider natural explanations far more likely given the immense energies and vast distances involved. Beyond the mystery of their source, the bursts themselves carry a hidden message in their structure. As an FRB travels across the vast intergalactic medium, it does not arrive all at once. The lower frequency radio waves are slightly slowed down by the thin plasma they pass through, a delay called dispersion. By measuring how much the lower frequencies lag behind the higher ones, astronomers can calculate the total amount of material the signal has traveled through. Each burst becomes a cosmic probe, allowing us to literally weigh the invisible atoms floating in the vast spaces between galaxies. This turns every detection into a dual discovery, a puzzle about an extreme event, and a tool for mapping the universe's hidden scaffolding. The sheer brevity and power of FRBs challenge the limits of our astrophysical models. How can any object, even a magnetar, concentrate so much energy into such a vanishingly short instant? Their existence forces us to consider physics operating under conditions we cannot replicate, in environments of gravity and magnetism beyond our imagination. They are the universe's most powerful and most cryptic radio transmitters, broadcasting messages we are only beginning to decode. And as we listen for these sudden, explosive shouts from the dark, another anomaly asks us to tune our ears to something entirely different, a steady, pervasive hum that seems to underpin the cosmos itself. The cosmic microwave background is the oldest light in the universe, a snapshot of the infant cosmos just 380,000 years after the Big Bang. For the most part, this afterglow is remarkably smooth, a nearly uniform sea of microwaves bathing the entire cosmos, with only tiny, expected variations in temperature. This smoothness is a cornerstone of our understanding of cosmic inflation, the idea that the universe underwent a period of unimaginably rapid expansion in its first moments. Yet, when scientists created the most detailed maps of this ancient light using satellites like WMAP and Planck, they found a blemish that defies this narrative of uniformity. In the constellation Eridanus, there exists a region about 70 microkelvins colder than its surroundings. That temperature difference may sound minuscule, but the size of this cold spot is staggering, spanning 1 billion light-years across. The chance of such a large, cold feature appearing randomly in our otherwise smooth cosmic baby picture is less than 1 in 200. This is not a minor imperfection. It is a cosmic anomaly on the grandest scale, a shadow in the first light of creation. So what could cast such a shadow? The leading explanation is a supervoid, a truly colossal region of space that is mostly empty, a bubble in the cosmic web containing far fewer galaxies and clusters than expected. According to a key prediction of general relativity known as the integrated Sachs-Wolf effect, light passing through such an immense underdensity on its journey to us would lose a tiny amount of energy, shifting it to a slightly colder temperature on the cosmic microwave background map. It would be like the light climbed out of a deep gravitational well, getting tired and colder in the process. The search for this proposed supervoid, however, has yielded mixed and confusing results. Some surveys have indeed found a large underdensity in the general direction of the cold spot, but its size and emptiness do not seem sufficient to explain the full depth of the cold signal we observe. The numbers do not quite add up, leaving a gap between the observed effect and the proposed cause. This discrepancy has opened the door to far more exotic possibilities. Some cosmologists suggest the cold spot could be a bruise, a signature of a collision with another universe in a vast multiverse. In such a scenario, the bubble of our expanding universe might have bumped into another bubble during inflation, and the energy of that collision could have left a permanent, cooler imprint on our cosmic microwave background. Others propose it might be evidence of a topological defect, a cosmic texture left over from a phase transition in the early universe, a kind of frozen knot in the fabric of space-time itself. The cold spot endures because it probes the very limits of our standard model of cosmology. It asks a profound question: is this giant shadow simply a rare statistical fluke in an otherwise predictable cosmos? Or is it a genuine crack in the model, a signpost pointing to physics beyond inflation? It reminds us that even our most cherished maps of the universe's beginnings may contain within them clues to realms we have not yet dared to imagine. This large-scale imperfection in the universe's first portrait naturally leads us to wonder about imperfections in the forces that bind reality itself, forces that seem, against all expectation, to be perfectly tuned for our existence. Even the most fundamental building blocks of matter can hide profound surprises. For decades, scientists believed they had a precise measurement for one of nature's most basic constants, the charge radius of the proton. This number describes the spatial extent of the proton's positive charge, essentially how big it appears to other particles. It is a cornerstone value, plugged into countless equations in nuclear physics and quantum electrodynamics, the theory that describes how light and matter interact. The established value came from two trusted methods: scattering electrons off protons and studying the energy levels of ordinary hydrogen, where an electron orbits the proton. These methods agreed beautifully, painting a consistent picture of the proton's size. Then, in 2010, a team of physicists performed a seemingly straightforward but revolutionary experiment. They created an exotic form of hydrogen, not with an electron, but with a muon orbiting the proton. The muon is often called the electron's heavier cousin, identical in every way except it is about 200 times more massive. This greater mass means the muon orbits much closer to the proton, effectively acting as a far more sensitive probe of the proton's internal structure. By using laser spectroscopy to measure the subtle energy jumps of this muonic hydrogen, the researchers could calculate the proton's charge radius with unprecedented precision. The result sent shockwaves through the physics community. The proton, according to the muon, was about 4% smaller than everyone had thought. In the world of quantum precision, where measurements are often accurate to many decimal places, a 4% discrepancy is not a small rounding error, it is a chasm. It is the difference between a map being perfectly accurate and being off by an entire city block. This was the birth of the proton radius puzzle, a decade-long controversy that remains unresolved. Why would the proton appear to have a different size when measured by a muon versus an electron? One haunting possibility is that our understanding of quantum electrodynamics, one of the most successful and rigorously tested theories in all of science, might have a subtle flaw that only reveals itself under these extreme conditions. Another, even more exciting prospect is that this discrepancy points to the existence of unknown particles or forces that affect muons differently than they affect electrons. Perhaps a yet undiscovered particle mediates an interaction that slightly alters the muon's energy levels, tricking our measurements. The physics community responded with a wave of meticulous new experiments. Teams went back to the traditional electron scattering methods, refining their techniques with incredible care. Others performed spectroscopy on different exotic atoms. The latest results have added layers of intrigue, with some newer measurements leaning toward the smaller muonic value, while others still hold to the larger traditional number. The puzzle has not been solved, it has deepened. This conflict over a fundamental constant is not just academic nitpicking. The proton is a primary component of every atomic nucleus in our bodies and in every star. If we do not understand its basic size, it suggests there is a piece missing from our understanding of how all matter is structured. It is a whisper from the quantum realm, hinting that even in the seemingly settled world of subatomic particles, new physics may be lurking just beneath the surface, waiting to be revealed by the persistent scrutiny of a heavier, more sensitive cousin to the electron. This intimate discrepancy in the heart of matter compels us to look up once more to examine how light itself, the messenger of the cosmos, may carry its own strange inconsistencies across the vastness of space. The precise heartbeat of the cosmos is measured by a single number, the Hubble constant. It tells us how fast the universe is expanding at this very moment, the rate at which galaxies are receding from one another. Pinpointing this number has been a century-long quest, a cornerstone of cosmology. Today, we have two independent, exquisitely precise ways to measure it. One looks back to the universe's infancy, the other examines its recent history, and they are telling us two different, irreconcilable stories. This is the Hubble tension, and it is not a minor disagreement. It is a full-blown crisis that threatens to unravel our most fundamental model of the cosmos. The first method uses the cosmic microwave background, that ancient afterglow from the Big Bang captured in stunning detail by the European Space Agency's Planck satellite. By analyzing the subtle patterns in this baby picture of the universe, scientists can work backwards through 13.8 billion years of cosmic evolution, using our standard model of cosmology to predict what the expansion rate should be today. This early universe measurement gives us a very specific, highly confident number. The second method uses cosmic mile markers within our local universe. Astronomers observe pulsating stars called Cepheid variables and certain types of supernova in relatively nearby galaxies. Because we know the intrinsic brightness of these objects, we can measure their distance precisely, and by comparing that to how fast they are moving away from us, we get a direct local measurement of the Hubble constant. This late universe measurement, championed by teams like the one led by Nobel laureate Adam Rees, also gives a highly confident number. The problem is stark. The local measurements consistently suggest the universe is expanding faster by about 5 to 10% than the early universe data predicts. Imagine two of the world's most accurate clocks, built by master watchmakers using different but trusted blueprints. You set them at the same moment. One clock runs on the physics of the universe's first moments, the other on observations from its recent life. After billions of years, they should show the same time. They do not. One is ticking noticeably faster. This discrepancy is now at a level of statistical significance that is extremely hard to dismiss as mere chance or error. As cosmologist Wendy Friedman has noted, this tension is arguably the most exciting thing in cosmology right now because it is a clear signal. It is the universe telling us that our standard model, known as lambda cold dark matter, is incomplete. We are missing a key ingredient in our recipe for reality. The proposed solutions are as fascinating as the puzzle itself. One leading idea is early dark energy, a speculative form of energy that could have briefly surged and faded in the universe's first few 100,000 years, subtly altering the initial conditions that Planck measures and throwing off its prediction for today's expansion. Another possibility involves exotic properties of neutrinos, perhaps that these ghostly particles are more massive or interact in stranger ways than we thought, which would affect how structures form and thus the expansion history. There is also the humbling possibility of a hidden systematic error, an unknown bias in one of the measurement chains that has eluded the world's best minds. Yet after years of intense scrutiny, the error bars have only shrunk and the tension has grown more severe. This is not a problem with the data, it is a problem with the theory. The Hubble tension forces a profound realization. Our cosmic timeline, from the first flash of the Big Bang to the galaxies we see today, may have a chapter we have not read or a force we have not accounted for. It suggests the laws governing the universe's expansion are not as constant as we believed, that something changed along the way. This fundamental disagreement about the very pace of cosmic growth echoes a different kind of defiance, one found not in the laws of physics, but in the ancient structures those laws seem to have built too soon. The smooth cosmic tapestry predicted by our best models is fraying at the edges. In 2021, astronomer Alexia Lopez was analyzing the light from distant, brilliant quasars when she noticed an impossible pattern. Stretching across 1/15 of the observable universe, a nearly symmetrical, crescent-shaped arrangement of galaxies, galaxy clusters, and gas clouds came into focus. This is the Giant Arc, and its scale is almost incomprehensible. It spans 3.3 billion light-years, a structure so vast it would take a beam of light, moving at the universe's ultimate speed limit, over 3 billion years just to travel from one end to the other. To put that in perspective, our entire Milky Way galaxy is a mere speck 100,000 light-years across, lost within this cosmic architecture. The existence of such a structure directly challenges a foundational pillar of modern cosmology known as the cosmological principle. This principle states that on the largest scales, the universe should look roughly the same in every direction and from every location, a homogeneous and isotropic soup of matter. There should be no grand designs, no preferred directions, no structures that stand out as unique landmarks on the cosmic map. The Giant Arc is not just a landmark, it is a continent. According to our standard models of how the universe evolved after the Big Bang, there is a theoretical size limit, about 1.2 billion light-years, beyond which such coherent structures should not have had enough time to form under the influence of gravity alone. The Giant Arc is nearly 3 times that limit. Its discovery forces a difficult question: is this a statistical fluke, a rare but permissible alignment in the cosmic lottery, or is it a genuine feature that our models cannot explain? The analysis suggests the odds of such an alignment occurring by random chance are vanishingly small, less than 1 in 100,000. This has ignited a fierce debate within the cosmology community. Some researchers argue that while extraordinary, the arc might still be a rare density fluctuation within the accepted framework, a cosmic skeleton in the web of filaments that connects all matter. Others see it as a potential crisis, a sign that our understanding of the early universe's structure formation is missing a crucial ingredient, perhaps a primordial magnetic field or a different type of dark matter that seeded larger patterns. This is not the only contender for a universe-breaking megastructure. Another, called the Hercules Corona Borealis Great Wall, is a colossal cluster of galaxies spanning an estimated 10 billion light-years, though its exact boundaries and coherence are still debated. The very fact that we are having this debate is telling. Each new survey of the sky with ever more powerful telescopes pushes the boundaries of what we thought possible. These potential megastructures are like discovering the foundations of a city larger than the country it sits in. They force us to redraw our maps of cosmic evolution. They hint that the universe's largest-scale structures might be more intricate, more organized, and perhaps more ancient than our theories allow. If the cosmos can sculpt arcs of such impossible scale, what other patterns might be hidden in the darkness, waiting for a patient observer to connect the dots? While these structures define the universe's grand architecture, the next anomaly presents a signal not of scale, but of startling precision, a rhythmic pulse that arrives with the regularity of a cosmic metronome. A solitary, silent vigil for cosmic companionship was broken by a shout. On August 15, 1977, the Big Ear radio telescope at Ohio State University was performing its routine scan of the sky, listening to the static hiss of the universe. The next day, astronomer Jerry Amon was reviewing the computer printout, a long column of alphanumeric codes representing signal strength. His eyes stopped at a sequence reading 6EQUJ5. Circling it in red pen, he wrote a single, emphatic word beside it: wow. For 72 seconds, the telescope had recorded a powerful, narrowband radio signal at exactly 1420 MHz, a frequency that is notably quiet, protected from natural astrophysical processes, and sits right in the waterhole, a band considered ideal for interstellar communication. The signal rose and fell with the perfect profile of a celestial source passing through the telescope's fixed beam. It had all the hallmarks of an artificial, extraterrestrial broadcast. And then it vanished, never to be heard again despite decades of dedicated follow-up. The WOW signal became an icon, a ghost in the machine that perfectly mimicked what scientists had hoped to find, yet offered no proof, no repetition, and no explanation. It stands as the most tantalizing and frustrating anomaly in the history of the search for extraterrestrial intelligence, or SETI. Modern searchers have refined the process immensely, deploying algorithms to sift through millions of signals in real time, filtering out the relentless noise of human technology and natural cosmic events. This rigor was tested recently with the detection of BLC-1, a seemingly promising narrowband signal that appeared to originate from the direction of our nearest stellar neighbor, Proxima Centauri. The excitement was palpable, but the scientific method is built on skepticism. A meticulous investigation revealed the signal's characteristics shifted in a way inconsistent with a source moving with the star. The culprit was likely human radio interference, a subtle form of terrestrial noise that mimicked a celestial origin. This outcome, while disappointing, is instructive. As SETI researchers and astrobiologists note, the vast majority of candidate signals resolve into human-made sources or rare but natural astrophysical phenomena we do not yet fully understand, like yet unknown forms of stellar activity or interactions with interstellar plasma. The enduring power of the WOW signal and its modern echoes lies not in providing answers, but in framing the ultimate question. It forces us to confront the profound silence of the cosmos with a single, brilliant counterexample. That one perfect burst, never repeated, drives the entire philosophical engine of SETI. It reminds us that a universe capable of such a perfect, teasing whisper is a universe where the possibility of a deliberate hello can never be entirely ruled out. This search for a signal, for a presence, makes the next anomaly all the more haunting because it is defined not by a mysterious message, but by a deafening, universal silence. Our galaxy's heart holds a secret written in high-energy light. For eons, the Milky Way's bustling center was thought to be a relatively quiet neighbor, its supermassive black hole, Sagittarius, a star slumbering peacefully. Then, in 2010, the Fermi Gamma-ray Space Telescope unveiled a breathtaking and violent truth. It revealed two colossal, symmetrical bubbles of gamma-ray radiation, each towering 25,000 light-years above and below the galactic plane. These are the Fermi bubbles, and they are monumental. If our eyes could see this ferocious gamma-ray light, the structures would span half the visible night sky. They form a near-perfect hourglass shape centered on the core, their edges remarkably sharp, as if carved by a sudden, titanic event. The discovery was a complete surprise, a hidden chapter of our own galaxy's biography suddenly illuminated. The bubbles are filled with ultra-fast-moving particles, and their sheer scale points to an explosion of energy from the galactic center that occurred sometime in the last few million years, a mere blink in cosmic time. But the bubbles are not the only mystery. Nestled within them, emanating directly from the dense core itself, is another puzzling signal, the galactic center excess. This is a diffuse, spherical glow of gamma rays that cannot be explained by any known astrophysical sources, like spinning neutron stars or the remnants of supernova explosions. Its spectrum, the specific fingerprint of its energy, is smooth and featureless, which makes it incredibly intriguing. One compelling explanation points back to the dormant giant at our center. Astrophysicists suggest that several million years ago, Sagittarius, a star, might have undergone a period of intense activity, feasting on a large cloud of gas and dust. This feast could have generated powerful, bipolar jets of material shooting out perpendicular to the galactic disk, inflating these giant bubbles and accelerating particles to near light speed. The echoes of that ancient cataclysm would be the gamma-ray glow we see today. This is a story of a sleeping dragon that once roared. However, there is another, even more profound possibility whispered by the data. The smooth, spherical nature of the galactic center excess perfectly matches a prediction from particle physics. If dark matter is made of weakly interacting massive particles, then where those particles are densest at the very heart of the galaxy, they should occasionally collide and annihilate each other. Such an annihilation would produce, among other things, a cascade of gamma rays with a very specific energy signature. The excess we see could be the first indirect glimpse of dark matter's true nature, the ghostly signal of invisible particles meeting their end. Distinguishing between these two stories, the astrophysical outburst and the particle physics signature, is one of the great detective challenges in modern science. Researchers meticulously analyze the exact shape of the gamma-ray energy spectrum and the spatial distribution of the glow, looking for subtle clues. A jet from the black hole might leave a slightly different imprint than a spherical cloud of annihilating particles. So far, the evidence remains tantalizingly ambiguous. The Fermi bubbles and their mysterious core glow represent a duality, a cosmic either-or that sits at our doorstep. They are either a monument to a violent event in our galaxy's recent past, a reminder that our quiet neighborhood was once a scene of unimaginable energy, or they are the first faint signal from the universe's dominant but invisible substance, a beacon from the dark. This energetic puzzle emanating from our own galactic core shifts our perspective from the colossal to the infinitesimal, to the particles that supposedly fill the empty void of space itself. The recipe for the universe's first matter was thought to be elegantly simple. In the searing heat of the Big Bang's first few minutes, a process known as Big Bang nucleosynthesis fused the primordial soup of protons and neutrons into the lightest atomic nuclei, primarily hydrogen and helium, with a tiny, predictable trace of lithium. For hydrogen and helium, the predictions match the observed cosmic abundances with stunning precision, a triumph for cosmology. But for that third element, lithium, the numbers tell a different story. The oldest stars in our galaxy, known as population 2 stars, act as pristine cosmic fossils. Formed from nearly pure material left over from the Big Bang, their atmospheres should preserve that original lithium signature. Yet when astronomers measure it, they find only about 1/3 of the lithium-7 that our best models insist should be there. This is the cosmological lithium problem, a discrepancy that has persisted for decades, quietly undermining our confidence in the universe's first nuclear forge. To understand why this is so puzzling, you have to appreciate the precision of the prediction. Big Bang nucleosynthesis is not a vague sketch. It is a detailed, quantitative calculation based on well-understood nuclear physics and the known conditions of the early universe. The amount of each light element produced depends critically on the density of ordinary matter and the expansion rate during those first minutes. The fact that hydrogen and helium align so perfectly tells us we have the broad picture right. The lithium mismatch, however, is a glaring outlier, a single wrong ingredient in an otherwise perfect cake. It suggests something subtle but important is missing from our equations. Could our understanding of the nuclear reaction rates themselves be slightly off? Some nuclear astrophysicists have proposed that certain rare reaction pathways involving beryllium or helium, which would destroy lithium, might have been more efficient than our laboratory measurements suggest. Others look to the stars themselves. Perhaps these ancient stellar fossils are not perfectly pristine after all, their surfaces slowly churning and dragging lithium down into hotter interior layers where it is destroyed, effectively hiding the evidence from our telescopes. The most intriguing solutions, however, reach beyond conventional astrophysics into the realm of exotic particles? What if unknown physics altered the conditions during those crucial first minutes? Some theorists have explored whether hypothetical particles like actions, which are also candidates for dark matter, could have been present. These particles might have provided an additional energy source or subtly changed how neutrons and protons interacted, tweaking the nuclear chain reaction just enough to produce less lithium. Alternatively, decaying exotic particles from an even earlier epoch could have injected extra neutrons, shifting the nuclear balance. Each proposed fix is a delicate operation, however, because it must lower the predicted lithium abundance without ruining the perfect agreement we have for hydrogen and helium. This makes the lithium problem a fiendishly tight constraint, a puzzle where the missing piece must fit an extremely precise whole. Ultimately, this is more than a debate about one element's abundance. It connects the largest scales of cosmology to the smallest scales of nuclear and particle physics. It asks whether our maps of the universe's first 3 minutes are complete. The lithium deficit is a whisper from an era before stars or galaxies existed, a signal that our reconstruction of that primordial forge, for all its successes, may still lack a fundamental component. It reminds us that even our most robust cosmic stories can harbor a single, persistent inconsistency that points toward deeper truths. This elemental puzzle shifts our focus from what the early universe created to how the structures within it move, revealing an alignment on a scale that seems to defy random chance. The final anomaly may be the most philosophically unsettling of all. Light does not just travel, it carries a hidden orientation, a property called polarization that describes the direction of its vibrating electric field. Normally, this polarization is random, scrambled by its long journey. Yet when astronomers studied the light from extremely distant quasars, the brilliant cores of active galaxies powered by supermassive black holes, they found something impossible. Over billions of light years, the polarization axes of these quasars appeared to show a curious alignment with each other, and even more strangely, with the large-scale structure of the universe itself. It was as if countless cosmic lighthouses, separated by voids of unimaginable emptiness, had somehow agreed to point in similar directions. The initial discovery, led by researchers analyzing data from the European Southern Observatory, sent a shockwave through cosmology. The alignment spanned distances so vast they should be causally disconnected, meaning no signal, not even light, could have traveled between them to coordinate this orientation since the beginning of time. This directly challenges the cosmological principle, the bedrock idea that the universe is isotropic, or the same in all directions on the largest scales. If the universe has a preferred direction, a cosmic grain, then our entire framework for understanding its origin and evolution requires a radical rewrite. The scientific response has been one of intense scrutiny. Could this be a subtle systematic error, a bias introduced by our instruments or by how the light interacts with dust in our own galaxy? Teams are now gathering much larger datasets, mapping the polarization of hundreds of thousands of quasars to see if the pattern holds or dissolves under greater statistical weight. If it persists, the explanations venture into extraordinary territory. One possibility involves primordial magnetic fields, woven into the fabric of the cosmos during its infancy and stretched to intergalactic scales by inflation. These fields could subtly influence the polarization of light traveling through them for eons. An even more profound idea suggests the alignment could be a fossil, an imprint from a time before the Big Bang. Some models of a cyclic or multiverse cosmology propose that our universe inherited a preferred structure from a prior cosmic phase, a kind of cosmic memory etched into the geometry of space-time itself. This would mean the Big Bang was not a true beginning from nothing, but a transition from a prior state whose influence we can still detect. The implications ripple through everything. It touches our understanding of cosmic inflation, which was meant to erase all such prior directional information, creating a smooth, isotropic universe. If this alignment is real, inflation may have been less effective, or perhaps something else entirely shaped our cosmic dawn. This single observation, this whisper of coordinated light across the cosmos, forces us to confront the most fundamental questions of all. Did our universe have a predecessor? Is there a structure to reality even larger than our observable cosmos? The alignment of quasar axes is not just another puzzle. It is a potential window into the ultimate architecture of existence, a hint that the story we tell ourselves about the universe's birth may be missing its very first chapter. These 15 cosmic whispers are not isolated riddles. They form a single, thunderous question about the nature of reality itself. Look at the patterns emerging from the darkness. The ghostly pull of dark matter on galactic edges and the phantom push of dark energy across the cosmos both point to a universe dominated by components we cannot see or touch. The proton radius puzzle and the lithium deficit suggest that even our most precise maps of the atom and the early universe are subtly, yet undeniably, incomplete. The impossible scale of the giant arc and the eerie alignment of distant quasars challenge the foundational principle that the cosmos is smooth and featureless on the largest scales. Each anomaly is a crack in the edifice of modern physics, and together they reveal a web of interconnected crises. They hint at new particles, unseen forces, or perhaps a fundamental rewrite of the rulebook for gravity and space-time. This is not science failing, it is science working exactly as it should. History is filled with such moments of beautiful confusion. For decades before Einstein, astronomers were puzzled by the orbit of Mercury. The innermost planet's path around the Sun ever so slowly rotated, a tiny drift that Newton's laws of gravity could not fully explain. This was a pre-revolutionary anomaly, a quiet signal that something was missing. It was only with the advent of general relativity, with its revolutionary vision of gravity as the curvature of space-time, that Mercury's dance was perfectly explained. That small puzzle was a signpost to a much larger truth. Today, we stand before a forest of such signposts. Philosophers of science note that this is how understanding truly advances. Periods of normal science where theories are refined and applied are eventually punctuated by these cascading anomalies that the old framework cannot digest. They force a period of extraordinary science, of creative chaos and daring new ideas. The current tensions in cosmology between the early and late measurements of the universe's expansion, between the predicted and observed large-scale structure, are the growing pains of a potential paradigm shift. We may be on the cusp of a transformation as profound as the advent of quantum mechanics or relativity, where the universe reveals itself to be stranger, more connected, and more magnificent than we ever dared to suppose. These deep space anomalies are not merely curiosities for specialists. They are symptoms of a deeper, more complete story waiting to be told. A story written in the motion of stars, the whisper of ancient light, and the silent architecture of the void. The true measure of our knowledge is not in the answers we hold, but in the questions that still shake the foundations of what we think we know. We have journeyed together through 15 cosmic rebellions, from the ghostly grip of dark matter to the impossible alignments of ancient light. Each one stands as a defiant beacon, not of scientific failure, but of a deeper truth waiting to be uncovered. This vibrant, unfinished quest is the very engine of discovery, reminding us that the cosmos is far more dynamic and mysterious than any single model can contain. The collective weight of these anomalies is a powerful signal. It tells us that the next great leap in understanding will likely come from connecting these disparate puzzles. Perhaps the key to dark matter will also resolve the lithium deficit, or a new theory of quantum gravity will finally explain both the universe's accelerating expansion and the strange alignments in its oldest light. Future discoveries, a direct detection of a dark matter particle, a new understanding of dark energy's nature, a unified framework that marries the very large with the very small will not just add a footnote to our textbooks. They will rewrite entire chapters of our cosmic story. Let this exploration serve as a lasting reminder of the humility and profound wonder required to truly gaze into the abyss. The universe invites not passive observation, but active, relentless curiosity. We would love to hear which of these cosmic mysteries resonates most deeply with you. Does the silent tug of dark matter intrigue you, or does the perfect, unanswered whisper of the wow signal capture your imagination? Share your thoughts in the comments below. For more journeys to the very edge of understanding, be sure to subscribe. The greatest secrets of the cosmos are not locked away in what we already see, but are hidden patiently within the very anomalies that defy our current grasp. The map is not yet drawn, and the adventure has only just begun.